All right. Good morning, folks. Hopefully, everybody's able to get the this problem done from yesterday. Hopefully, everyone's doing well. I've only seen a couple of you after school, so please make sure you stop by and get the next help if you need it. Um, I'll be making an announcement about a quiz next week, so we'll have a quick quiz on this chapter next week. I will ask that we meet on Monday, so let's go ahead then and we'll meet on Zoom Monday. That way, then I can explain to you what we'll use to do the quiz. Folks, make sure everyone gets onto Edmodo, register for Edmodo because I will be using that one for the quiz. And so the quiz next week will be on chapter 12, and the questions can range from anything we've done from the very beginning through resident. I'm sorry, through uh, molecular structure that we'll talk about today. Okay, and so please on Monday. So on Monday, we're going to meet in lieu of a video for Monday. We're going to meet at our class time, which starts at 10:35. We'll meet. I'll explain Edmodo to you. We'll take a practice quiz using Edmodo, and then I'll explain to you the procedures that we'll use, and then roughly Tuesday or Wednesday of that week, we'll go ahead and we'll take a quiz. Okay, and the quizzes will be live, so we will meet for the quizzes, and so I'll go through the procedures with you on Monday. Okay, so remember the exams I've postponed till after the AP. The exams for our class I've postponed till after the AP exam. That way, it gives us time to cover the material, and then once we are done with the AP exam, then we'll see how things work out with school. But if we have to, we'll take the exams through Edmodo as well. Okay. All right. So with that said, then let's go ahead and let's pick up where we left off with here yesterday. We were talking about formal charges, and so formal charges are basically a way that a method we can use to determine then which structure that we will use for a particular molecule, which structure that we will use to represent that particular molecule. Okay, so for example, we have carbon dioxide here. We have two equivalent structures. That means both of these structures meet up with all of the rules that we've assigned to draw Lewis dot structures here. And so the question then is, which of these structures then would be the one that we accept as being the structure for carbon dioxide? And we'll need the structures here for carbon dioxide when we start the discussion of VSEPR and molecular structure in just a moment. So you have to make sure you get the correct Lewis dot structure. But the question then is, of these two structures, which one would be more valid? The one then in which you have a triple bond between carbon and oxygen on one end and a single bond on the other end. Okay? And if you count all these, if you count all the electrons, each oxygen will have its octet, the carbon will have its octet, and furthermore, then if you look at this structure here, all of the valence electrons are accounted for. So this is a valid structure right here. So you have a triple bond between this oxygen and the carbon and a single bond here. Okay. So is the correct structure for carbon dioxide this one with a triple bond and a single bond, or this one here with two double bonds? Okay. Well, that's where the formal charges come into play. Formal charges then are a very simple method that we can use to assess the validity of a structure. And based on the formal charges, we go ahead and we assign then which structure we will use to represent that particular compound. Okay? And so it's a very simple calculation. Hopefully you had a chance to do the homework last night. Hopefully you were able to do this problem okay, and it looks like many of you were. Okay, so basically, when you find the formal charges, you are going to be counting electrons. You're going to be counting valence electrons for the atoms, and then making sure that you compare the valence electrons that it has when it's all by itself to the valence electrons that it has when it's part of a compound. Okay. All right. So with that said, let's go ahead and let's work through this really quickly. Okay. Let's work through this here. So for this structure here, we'll go ahead. Then we're going to find the formal charge for carbon. Okay. We will find the formal charge for this oxygen here, and we're going to say that this oxygen is different than this oxygen. We see that they're different. Why? Because they're bonded differently. They will have different they'll have different valence electrons when they bond to carbon here. So we'll call this oxygen 1, and we'll call this oxygen 2. And we need to find the formal charges for each of those oxygens because they are, even though they are both oxygens, they are bonded differently to the carbon. So therefore, the electron environment here is going to be different for this oxygen versus this oxygen here. Okay. All right. So with that said, let's go ahead and start out with carbon. Remember, first of all, what we need then is we need the total number of valence electrons for carbon. So again, not the overall, not all of the electrons. So we're not counting all of the electrons. We're just counting the number of valence electrons that carbon has. So make sure you keep that in mind. Okay. All right, so we have then 4 valence electrons for carbon when it's an atom all by itself. Okay. From that number, we will subtract the number of electrons that carbon has when it's a part of this molecule. And how do we account for that number of electrons? Well, we total up the number of lone pairs that the atom has with the number of bonds that the atom has as well. And with the bonds, because those electrons don't completely belong to it, we just take half of those electrons. Okay? All right, so with carbon here, it has no lone pairs, but it does have 1, 2, 3, 4 bonds, which represents 8 total electrons. Remember, only half of those go to the carbon. So therefore, in this molecule here, carbon has only 2 electrons that, 4 electrons that belongs to it. Okay, so it's 4 electrons that belong to it. So we'll go ahead and write that down. Okay. And thus the formal charge on this carbon is 0. So remember, when it comes to formal charges, the atom that has the formal charge, the ideal then is to make sure that the atom has a formal charge of 0. So in that particular structure, in this structure here, carbon has a formal charge of 0, and that's a good thing. Okay, so so far so good. Okay, this structure seems to be good so far because we have this atom having a formal charge of 0. Now let's go ahead and do the oxygen atom. Okay. All right, so this oxygen atom here, let's go ahead. Oxygen has 6 valence electrons when it's all by itself. From that number, we're going to subtract the number of valence electrons that this oxygen has when it's a part of this molecule. So it has 2 lone pairs, so 1, 2. It has 1, 2, 3. Okay, so it has 6 pairs that it shares with the carbon. Only half of that goes to it, so therefore it will have a number of electrons of 5. Excuse me, when it's a part of this atom. So therefore, oxygen in this particular molecule, this oxygen here, will have a +1 charge. Okay, and now that's not so good. The fact that oxygen here has a +1, we said that, remember, if a formal charge, a positive formal charge does occur, it should probably reside with the less electronegative atom. Here, oxygen is more electronegative than carbon, and yet it has a +1 charge, a +1 formal charge. This right here is not a good thing. Okay, this here, having carbon with a 0 formal charge, that's good. Okay. Oxygen here with a +1 formal charge, that's bad. That's not good because oxygen is an electronegative atom. It does not, and you can kind of think about it this way, is it does not want to have a positive charge. It would prefer to have a negative charge if it had to. Okay, so that's the way you can think about these formal charges. And again, formal charges don't represent actual charges, but we can kind of think about it in that way when we go about assessing what we have here. Okay. All right, so with that said, so that makes this not a good thing right here. So this structure right here, based on this oxygen, not so good. But again, we'll still have to decide what the formal charges are on this atom here, on this molecule here, to decide which of the two would be best. Okay. All right, let's go ahead and find the formal charge on this oxygen then. And I think if you remember what we did from yesterday, we're going to get for this the formal charge of -1, but let's go ahead and work it out anyway. Okay, so oxygen has a 6 valence electrons when it's all by itself. Okay. It has 6 lone pairs here, so it has 6 electrons, and we're going to total up there 6 electrons that belongs to it, and half of this, which is 1, so therefore we have 7. So it'll have 7 valence electrons when it's a part of this molecule, and so therefore the formal charge on this oxygen is going to be a -1, and like I said, that's okay, that's good. Is to have a formal charge of -1 is not especially when it's on oxygen, that's not so bad. So far we have, of the formal charges on here, we have two formal charges that makes this molecule good, and this one is not so good. This one's going to make things bad right here for this structure, okay, in terms of the formal charges. right, let's go ahead and determine the, let's go ahead and let's calculate the formal charges for this molecule here. Okay, so carbon, we'll calculate the formal charge in carbon there. Double bonded oxygen, since both of these oxygens are double bonded, they are identical in the way that they interact with the carbon. We only have one type of oxygen here, so we only have to do that calculation once. Okay. All right, so therefore then we have formal charge, I'm sorry, number of valence electrons for carbon is going to be 4 when it's all by itself. From that, we're going to subtract then the number of valence electrons that it has when it's a part of this molecule here. It has no lone pairs again, so we have 1, 2, 3, 4, 8 total electrons that it shares. Only half of that goes to it, so it has a 4 formal charge when it's a part of this molecule. I'm sorry, has 4 valence electrons when it's a part of this molecule. So therefore, it has a formal charge of 0, which again is a good thing. So we also obtain a formal charge of 0 for the for carbon on that side. Okay, so far in terms of the carbons, both of them have 0 formal charge. Okay, let's go ahead and calculate then for the formal charge of oxygen in this molecule. Okay, and so again, 6 valence electrons for oxygen when it's all by itself. Okay. In this molecule, it has 4 here that belongs to 2 lone pairs, so 4 electrons. Okay, half of these 4, so it's going to be 6. So therefore, a total of 6 valence electrons when it is a part of that molecule. Okay, and so therefore, oxygen in this molecule, in this particular structure here, has a formal charge of 0, and both of them will have a formal charge of 0. And so therefore, that makes this molecule then very favorable in terms of its formal charge. Okay, and so the answer then is, if we take a look at this, so of these 2 structures, which one is more valid? Which one is the better choice for us? Well, it will be then that structure right there. Okay, so hopefully you were able to get that yesterday in terms of formal charges and work on that. Okay, all right. What I'd like you to do then is let's take a look at this this problem here. Okay. Do number 12 here, and what I would like you to do then is, if I'm asking you in this problem to write out all the possible structures, if possible structures, so write out all the possible Lewis structures for xenon trioxide. Now, this is an example of a compound that does form with a noble gas. So it's a very unstable compound to begin with. It doesn't like to be together, so it's highly explosive. But I want you to draw the structure for xenon trioxide. Okay. I want to give you a clue. So all the possible structures, I'm going to tell you then that there will be 8 possible structures. There's 8 total possible structures. Okay, so go ahead, take about 5 minutes here, folks, and try to write out all the possible structures that you can. I will post for you all the possible structures. I don't want to take our class time here to draw them all out, but I'll post for you the answer. I'll post for you all possible structures, and then you can compare your answers. I'm just going to take a few of them to analyze. Okay, so I'll take a few of them. I'll draw out a few, 2 or 3 of them, so we can analyze in terms of formal charges, and thus determine then which one is the most valid of the possible structures. Okay, right. So take about 5 minutes, folks. Draw the Lewis dot structures for this compound, and then we'll get back together and we'll go over it. Okay, go ahead and get started with it. Okay, so that was about 5 minutes. Let's go ahead then and let's work on this here. Okay, so very first thing we have to do in order to draw these structures, okay, we have to indicate then how many total valence electrons we have to account for. So xenon has 8 total valence electrons, and with the 3 oxygens here, we have to account for 26. Whatever our Lewis structures are, should have 26 total electrons in it. Okay. All right, so with that said then, I think one structure that you can draw here, I think the most obvious one that you're going to draw here, in which every atom will have its octet, will be xenon, in which xenon then will form a single bond with each oxygen. Each one of these single bonds will be a coordinate covalent bond, because xenon will contribute both of those electrons to form each bond. So the xenon oxygen bond then is going to be a coordinate covalent bond. So if you notice here, oxygen retains all of its electrons. It doesn't contribute anything to this structure here. So that's one possible structure. Why is this possible? So let's go ahead and count, make sure we have 26 total electrons. We have represented here with 1, 2, so 1, 2, 3. Each one of these has 3, so we have 9, 10, 11, 12, 13. There are our 26. So there is the structure there. On top of that, xenon maintains its 8 valence electrons and oxygen has its 8. So the octet rule. This seems to be a pretty good structure because every atom has its octet. Every atom has its octet, and we've also accounted for the 26 electrons. Okay. All right. However, we'll determine then how good this structure is by doing formal charges in a moment. Okay. Let's take a look at another structure here. Okay. An equally valid structure here for us would be this structure here, where we have xenon, okay, and it will share a double bond with oxygen here. Okay. This is another structure that we can draw. Okay, and one of those bonds is going to form from oxygen contributing a electron pair. So one of these would be a coordinate covalent bond from xenon. The other bond in this double bond will be a coordinate covalent bond from oxygen. Okay, so keep that in mind. Okay, and then we have oxygen here, single bonded to xenon, and another oxygen here, single bonded to xenon. And again, count to make sure that we have our 26. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 16 as well, 26 as well. Okay. All right, so one more structure. So that's 2 of the 8. Let me give you one more. Okay. Let's see what we have here. So let's xenon here now, double bonded to all of the oxygens. Okay, with its lone pair here. And make sure you draw, when you draw these structures, folks, make sure you draw in the lone pairs. And so I'm running out of time today, but when we talk about the VSEPR theory and molecular structure tomorrow, I'm sorry, Monday, Tuesday, I'm sorry, Monday we will meet. I will still post a video. I'll talk about this in just a moment, but I still want to post a video because I don't want to lose any time here. So I'll post a video that you will do for homework. Okay, but we'll meet in class to talk about the quiz. I'll take any questions you have, but I will still post a video for you to watch, and you can watch that for homework. Okay, so I'll mention that in just a moment. All right, so on Monday we'll talk about the molecular structure and VSEPR theory. So in doing so, please make sure you include the lone pairs as well, because they will be critical in the structure of a molecule. Okay, so let's check to make sure this structure is valid. Okay, so you have then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are our 26 electrons as well. So of these 3 structures, it would appear then that the first one would be the correct one, because in the first one here, all the atoms have their octet. Here, xenon seems to violate the octet, but remember, atoms that are larger atoms, they can extend their octet, and that's what we see here with the xenon in both of these cases here. Okay, and so with that said, then let's go ahead and to figure out then which of these structures is the more valid of the structures. Let's go ahead and do the formal charges. Okay, so formal charge for xenon, oxygen here, all 3 oxygens are equivalent, meaning that they are bonded and interact with xenon in exactly the same way, single bond with 3 lone pairs. So we'll just solve for 1. Okay, all right. So with xenon then, let's go ahead and write this down. Xenon has 8 valence electrons when it's all by itself. Okay, from that, we're going to subtract then the number of valence electrons it has when it's a part of this bond. So it has 2 that belongs to it, 2. And it's sharing these 6 here. So 2, 3, 4, 5. So it gets 1 from each. So it's going to have a 5 valence electrons when it's a part of this molecule here. Okay. And so with that said then, it will have a formal charge here of +3. Again, that's not a good thing, folks. So positive formal charge is never a good thing. So make sure you keep that in mind. But the single bonded oxygens here, again, I think most of you at this point will recognize whenever you have a single bonded oxygen, it will have a formal charge of -1. But I'll quickly just write that in here for us. Okay, so 6 valence electrons when it's all by itself. Okay, 6 here, 1 plus 1 from this bond here, so it has 7 valence electrons when it's a part of this molecule here. So it has a formal charge of -1. Okay, so in this particular molecule here, Each oxygen has a -1 formal charge, which is not a bad thing, which is fine. It's more electronegative. But here you have a xenon with a +3 formal charge, which is not good at all. Okay. All right, let's go ahead and let's take a look at this second structure here, and let's assess its formal charge. Okay, so xenon here, again, will have 8 valence electrons. Okay, let's go ahead. From that, we're going to subtract then the electrons that it has in this structure. So it has 1, 2. It has half of this, so it's going to be 1, 2, 3, 4, 5, 6. Okay. And so therefore, in this particular molecule here, xenon, in this structure, xenon has a +2 formal charge. So a lot better than this +3 here in this structure here. Okay. All right, so I won't calculate for these here because we know those are -1. But let's calculate for this oxygen here, which is a double bonded oxygen. I think from what we've done so far, you'll start to pick up on this as well. Okay, that this is going to be a 0 formal charge. But let's go ahead and calculate for it. Okay, so it'd be 6. Okay, so 1, 2, 3, 4, 5, 6. Okay, so those are as a 0 formal charge. And so therefore, if we take a look at the formal charge here, we have a +2 for xenon, which is not good, but it's gonna be better than a +3 here. We have a 0 here for this oxygen, which is very good, and then we have a -1 for each one of these here. Okay, so far this structure in terms of the formal charge is better than the first structure that we have here. Okay, all right, let's go ahead and assess the last one, and let's see what we have. Okay, so xenon in this structure here, let's go ahead and take a look at it. Again, 8 electrons when it's all by itself, 8 valence electrons. Okay, so when it's a part of this molecule, you have 1, 2, 3, 4, 5, 6, 7, 8. Remember, it has half of each one of these double bonds. So this is 4, 4, and 4. So it has 2, 4. 1, 2, 3, 4. It will have 2 here, 2 here, and 2 here. So it'll get 2 from each one of these, and so it has a total of 8 valence electrons, but it's a part of this molecule. And so therefore, in this structure, xenon has a formal charge of 0. Okay, so that looks pretty good, folks. And then we saw then with the oxygen here, a double bonded oxygen, it will always be 0. So therefore, you have 0 formal charge here, 0 formal charge here, 0 formal charge here, and a 0 formal charge for xenon as well. There is this structure is the most valid. Okay, of the 8 that you'll draw, that's the most valid structure for xenon trioxide. Okay. All right, so with that said, please make sure you draw the remaining, hopefully you have the remaining 5 structures. So this is 3 of the 8. I'll post the structures for the remaining structures for this particular compound for you. Please compare your answers, okay? Get the homework done for the, make sure you take a look at the homework that was assigned for this and try to get that done. Come by and see me if you have any questions about that assignment. Any questions about the formal charges, because on Monday we're going to continue on and we're going to start talking about VSEPR theory and molecular structure. So the PhET lab that I asked you to do, please make sure you have that with you when we do the lecture. And I'll remind you again of that on Monday. But so please, folks, on Monday during our class time, we will meet on our Zoom Meet page. So we will meet and we will go live on Monday. And then I will also post a video that you can watch for homework and get that done. Okay. All right, folks. So have a good weekend. Hopefully I'll see some of you after school today. And if I don't, I will see you folks then on Monday. Okay. Have a good weekend.